Thank you to Incogni for sponsoring this video. On a late afternoon in 2015, a Finnish researcher was staring closely as a bee slowly rolled a ball across a platform. He has spent the past several weeks trying to teach a bee to use a tool, and for the first time, it seemed to be working. His name is Professor Olli Loukola, and he has spent the past 10 years studying intelligence and cognition in bumblebees. Through his research, he has found that bees are not only able to use tools to obtain a reward, but are even able to solve surprisingly complex puzzles without prior training. In one experiment, bumblebees chose to carry an object through a maze because they seemed to recognize that it would help them access a reward at the end. This type of complex, future-oriented thinking has often been considered to be unique to humans and the most intelligent of vertebrates. But Professor Loukola's research shows that even tiny bees may be capable of this as well. So what exactly does it mean for a bee to use a tool, and what made Professor Loukola think that a tiny insect might be capable of this in the first place? Well, let's take a moment to introduce how all of this even began. Olli says he's always been fascinated by the animals around him. Even as a toddler, he would sit outside in the garden during the summer, wearing nothing but a diaper, staring at ants for hours as they moved across the ground. While other children were playing with toys, he would run his own little experiments, like giving ants tiny pieces of sugar to observe what they would do. As he grew older, he began spending time on his uncle's farm, and it was there that he became interested not just in all kinds of animals, but in the way they behaved. That interest followed him into university, where he spent his PhD years doing field work with the great tits and pied flycatchers across Finland. And in 2015, after his PhD, he moved from Finland to join a leading bee research facility in London, the Chitka Lab. Here they were teaching bees how to pull string to retrieve a flower reward, how to solve puzzles, and investigating how social learning occurred in the first place. And before long, Olli realized that these insects were far more complex than he had ever imagined. As he watched these bees perform such amazing things around him each day, he began to wonder if it was even possible for them to know how to use tools. So next, let's take a look together at how he tried to test this. To answer this question, we need to understand what scientists mean when they talk about tool use. At its core, tool use is just using a movable object to achieve a specific goal. That can be something as complex as using a stick to pull food closer, or as simple as moving an object to the right place to unlock a reward. With this in mind, Olli first went to a nearby craft store to try and look for different materials that he could use for his experiment. His first idea was to see whether bees could learn to use a toothpick to get sugar water out of a tube. But he soon realized that although the bees were willing to try, with some of them doing so for up to 20 minutes, the movements required were simply too precise. So he realized the tool had to be something the bees could move more easily. In the coming days, Olli would try showing different objects to the bees. And while Olli's busy designing his experiment, I want to take a moment to introduce today's sponsor, Incogni. One of the things that has gotten quite ridiculous over the last few years is the amount of scam calls and emails you end up getting every single day. It's gotten to the point where I pretty much don't answer any number that I don't recognize. This happens because our personal information, like our phone numbers and email address, ends up circulating online through data brokers. Incogni is a service that helps remove your personal information from these data brokers by contacting them and sending deletion requests on your behalf. One of their most powerful features is the custom removals feature, where you can simply send Incogni the link to a website that might be sharing your information, and Incogni will handle the rest. This can save you a lot of time from trying to do this yourself and allows you to have more control over what information about you is publicly available in the first place. If you want to give Incogni a try, you can check out Incogni at incogni.com/curiousburb and use the code curiousburb to get 60% off an annual plan. Thanks again to Incogni for sponsoring this video. Now let's get back to Olli's research. He found that with most objects, the bees tended to stay away and not approach them. But one day, when he placed a few small wooden balls on the platform, he noticed the bees began rolling them almost immediately. So he decided to build his experiment around that behavior. First, he would teach a bee to push a yellow ball into a hole at the center of the platform by using a plastic demonstrator bee. Once the ball was in the hole, he would open a hatch underneath, which would give the bee a sugar reward. He would repeat this several times before placing the bee on the platform with the ball alone. And as he watched closely, he noticed the bee immediately began rolling the ball towards the hole.
I was like telling to my colleagues, like, hey, come and see, like I trained my first bee to roll the ball, that they're using the ball as a tool. And then the people were like, yeah, sure, this crazy Finn is like doing his crazy stuff, and they didn't believe me. But then when they saw that, like, wow, this is huge. And they're like, wow, this is amazing. And Lars was like saying the same, like, hey Olli, did you know that this will be big?
It was in this moment that Ollie truly fell in love with bees, and he couldn't help but wonder what else these tiny creatures might be capable of. In the coming weeks, he expanded on the initial study by testing 9 more bees. These bees would be given the same training before being tested 10 times on a larger platform. And what he found was that all 9 successfully passed each time. And he also noticed that the bees took progressively less time to solve the task over trials. In comparison, he also had a control group that received no training and they failed every time. Now, this might seem like a fairly simple experiment, but Ollie was very excited by this, and as he watched these bees happily roll the balls across the platform, he started to ponder a far more complex question. How exactly does learning occur in their mind? See, humans are able to do something quite remarkable. We are able to learn simply through observation, and this is often considered to be an advanced form of social intelligence. So, are bees able to do something similar? For his next experiment, he would have different groups of bees observe the task get solved in 3 different ways. First, by a demonstrator bee who had previously passed the test. Second, by a ghost demonstrator where he would use a magnet to move a platform underneath the ball. And finally, with no direct demonstration at all. Instead, the bee would find the ball already at the center of the platform. In each of these scenarios, the observer bee would be given sugar water as a reward when the ball reaches the center. And there's an important detail here. During the demonstrations, there were 3 balls present, but only the furthest ball could be moved by the demonstrators. During the real test, however, any of the 3 balls could be used. After several demonstrations, the bee students were now ready for the real test. And what Ollie found was fascinating. First, all the bees that were taught by another bee instructor were able to successfully pass the test pretty much every time. In comparison, the bees that watched only the ghost demonstrators still did surprisingly well, passing around 80% of the time. And finally, the group which had the ball directly placed in the middle still passed around a third of the time. This may not sound like much at first, but it's probably the most remarkable result out of them all, because it suggests that the bees may have been able to infer what needed to be done simply by seeing the end result. But there's one more result that was even more impressive. During the demonstrations, the ball that was moved was always the furthest away from the center. However, when the bees actually went to perform the task, most of them went for the ball closest to the center instead. And this is fascinating as it shows that the bees weren't simply replicating the behavior from the demonstrations, but were actually able to understand how to solve the problem and even improve on the original demonstrations.
In the test where all these 3 balls were available and the observer bee actually didn't select the same ball that the demonstrator was using, but they selected the easier or the easiest option, the ball closest to the goal. And that was the first evidence that insects can actually emulate doing something better based on what they observed someone else doing.
When this footage aired, it attracted widespread interest from researchers and news outlets all across the world. People quickly fell in love with the idea of a scientist teaching bees to play mini-golf in his lab and were equally fascinated by what this experiment revealed about their intelligence. Eventually, in 2017, Olli parted ways with the Chitka lab to start his own lab back in Finland, and it was there that his research took another major leap forward. Back in Finland, Olli began thinking about what all of this really meant. He has spent the last few months traveling for lectures and speaking to the press, and he watched as his work spread all around the world. For most people, his work had already shown that bees were capable of far more than anyone had imagined. And yet, his experience over the years made him wonder if they might be capable of even more. This time, the bees would be put through something far more difficult, as Olli wanted to understand if they might even be capable of a form of abstract reasoning. First, the bees would be put through a training phase where they were presented with two different coloured balls on a platform. The bees were required to roll the ball which matched the platform's colour to the centre to receive a reward. Olli also had two additional groups of bees that went through the training with different colour combinations. After the bees were able to roll the corresponding ball to the centre 5 consecutive times, they considered to pass the training. And then came the most important part. After the bees had passed the initial training, they were now placed on a new platform with 3 different coloured balls. 2 of these had the same colours that were used during training, while the third ball and platform had a matching colour that was completely new to the bees. And each bee was given 10 minutes to try and solve the task. This new scenario tested whether the bees had the cognitive flexibility to apply what they had learnt to a new situation. Specifically, if the bees would learn to select the colour of the ball which corresponds to the new platform, even though they had never seen this colour before during training. And what he found was very interesting. The bees were able to solve the task, but not in all colour combinations. Almost all the bees that were trained on the blue and red platforms were able to pass when they were later tested on the yellow platform. While on the blue platform, none of the bees ended up passing the test, with most of them not wanting to even land on the platform itself. And finally, those tested on the red were somewhere in the middle. These results were completely different from what Olli had expected, and in the following weeks he would train another group of bees to be tested on the blue platform. But again, all of them avoided the blue platform. To try and understand why this was the case, I reached out to Professor Loukola to ask this very question. Why do you think that the bees weren't able to pass when they were tested on the blue platform?
We still don't know like what is the reason behind, but like I'm speculating something like the training history. If we train them with orange and yellow, and BC orange and yellow quite the same, like they're like in their visual, the yellow and the orange are quite close to each other, but then the blue is like on the opposite side. And maybe it's like causing the neophobia because it's like novel thing, novel color. And that's why they're like hesitating in the test, because now we know much more about the neophobia behavior or neophobia in bumblebees because of the new paper that we published in Science, where we show that some bees, they, even if you let them be in the arena like 20 minutes, they rather start sleeping than, touching the ball. But then if you pre-train them, they just like happen to know that the ball is something safe and something that they can move. Then, like in the test phase, they start moving the ball almost right away when they come into the arena.
So it seems there's a lot more to understand about what really goes on in the mind of a bee. But even with that in mind, this experiment suggested something remarkable. That under the right conditions, bees may be able to generalize what they have learned to a completely new situation, and Olli soon published this in a follow-up paper in 2022. But despite all this, there was still one question left in Olli's mind. All the experiments so far had asked the bee to do the same basic thing: move a ball into the right place for a reward. But we often use tools in many different ways, and soon he began to wonder if bees might be able to do something similar. To test this, Olli would turn to one of the most famous experiments in animal behavior, the box and banana experiment. This was an experiment initially done by German psychologist Wolfgang Köhler in the early 1900s to try and understand how chimpanzees come up with solutions to different problems. Here's how it works. First, the chimpanzees were placed in a room which was filled with wooden crates. In the middle of the room was a bunch of bananas suspended high in the air. In Köhler's experiment, the chimpanzees wandered around the room for some time and looked frequently between the bananas and the boxes. Then almost suddenly, they would start stacking the boxes underneath before climbing up to reach the banana. This study became a classic example not only of creative tool use in animals, but also of their ability for spontaneous problem solving. So Olli tried to adapt this for bumblebees. For his experiment, he would begin by placing the bees in a carefully constructed room. In the center was a blue flower with sugar water on top. The bees would enter through a corridor which was slightly obstructed by a styrofoam ball, and to get to the center, they would need to push this ball out of the way. He would repeat this several times, and this taught the bees two things: to associate the blue flower with a reward, and that the styrofoam ball was safe and easily movable. Now let's take a look at what he found.
So we now put the flower from the floor to the ceiling of that arena. And the arena was only 3 centimeters high, but it was just high enough that the bee couldn't fly actually. Bumblebees are quite clumsy in flying, so they cannot really fly in that small space. So the bee saw that flower on the ceiling, and the only way to get the reward was to move the ball underneath the flower and then climb on the ball and then reach the flower. So quite difficult task for the bee, right? And here we can see a sample video where the bee is in the arena and starting rolling the ball to the right well, then climbing on the ball and reaching the flower.
But we aren't done just yet, because while Olli had been conducting this experiment, his old colleagues at the Chitka lab found that bees seemed to have a weird obsession with balls. In one experiment, they noticed instead of running straight to food, the bees would choose to stop and roll around with the ball before continuing on, even though there was no incentive provided. That experiment is a story for another time, but when Olli saw this, he thought that maybe the bees simply solved the task by randomly rolling the ball around the arena.
If the bee starts rolling the ball into the arena, and then when they're coming closer to the flower becomes bigger in their visual field, and then that's kind of driving them to move the ball underneath the flower, and they might solve the task just by using simple associative mechanisms, which means that, yeah, the flower is becoming bigger in their visual field, and they're doing whatever in order to make that flower bigger in their visual field.
So he decides to take the experiment one step further. He will put a new group of bees through the same training, but this time there was a barrier between the ball and the flower. The bees would initially see the flower when they entered the room, but wouldn't have constant visual feedback while they were rolling the ball. He also had a control group of bees that didn't go through any training. Now let's take a look together at how the bees performed. This is the group that has gone through the initial training, and you can see that the bee cannot see where the flower is when it is initially rolling the ball. Pay very close attention to what the bee does. You can see that she immediately begins rolling the ball towards the flower. She runs into the wall a little on the way, but she manages to get it under the flower and climbs on it to drink nectar. And in a group of just 22 bees, Olli found that around 75% were able to solve the task successfully. In comparison, only 5% were able to pass in the group which received no prior training. And in a later experiment, Olli changed up the shape of the maze so that the bees had to choose which direction to roll the ball in. And again, a significant majority of the bees immediately began rolling the ball towards the area with the blue flower. These experiments marked a major leap from what Olli had found previously, and so just last month in June 2026, Olli published these findings in his most recent paper in Science. In it, he showed that bees may not only be able to use tools in a variety of different ways, but also had the capacity for a level of problem solving that had previously only been expected from primates. In the end, I couldn't help but ask Professor Loukola what it was like studying bees all these years, and if there were any interesting stories he might be able to share with us.
Yeah, of course, the most challenging part is like you really need like some you need to be patient because like some of the bees that they're like not motivated, they might start sleeping or if you like if you're scheduling your day and you say like, okay, I will test this bee like 3:30 and then I need to go home, and then the bee might actually start sleeping in the nest that's not willing to come. And so yeah, at least if you have like kids and you have to pick up the kids from the school, for example, you cannot really like call the school like, hey, I need to test this one bee, like I will be late like a couple of hours. It doesn't work like that. And then like if it's like low pressure outside, like the weather is like rainy or cloudy, the bees can sense that kind of thing inside the lab, and they're like sleepy as well. Like they like because in the nature, if it's rainy, they won't go out foraging that often. So these kind of things that if you don't know these things, you might like lose your mind because like, what is going on here? All the bees are sleeping. And I was like many times my students asking these questions, I was like, hey, look outside, it's rainy. Yeah, like if you start bumblebee stuff from the scratch, you will lose your mind because so many different things that might actually. Yeah.
Olli has often wondered why we seem so determined to place one species above another. For decades, intelligence was often treated as something hierarchical, with humans at the top and other animals arranged below according to how closely they resembled our abilities. But Olli has always seen things differently. He believes that every species has their own strengths that allow them to navigate their world. And over the years, he has been glad to see that public perception is slowly beginning to shift in that direction too. In recent years, science has increasingly revealed that intelligence can take shape in more forms than we once imagined. And through Olli's own research, he has shown that even tiny insects like bees can learn to use tools and solve complex problems in ways that many people once thought was impossible. When Olli reflects on his research over the years, he believes that one of his greatest strengths was his own naivety. Because he hadn't spent years learning what bees couldn't do, he allowed himself to ask the strange questions and try ideas others may have dismissed too quickly. In the end, that's the advice he gives not only to researchers, but to anyone trying to understand the world a little better. To stay open-minded and to not be afraid of having ideas that may seem a little ridiculous at first. And for Olli, this is only the beginning. Questions about consciousness, emotion, and pain in insects are still heavily debated, but with new tools like machine learning and motion tracking, we now have increasingly precise ways of measuring behavior, and Olli believes we're getting closer to answering those questions than ever before. So, what's the next step in terms of your research? Can you share anything with us about your future plans?
And now we have some new plans to kind of continue with using the similar kind of setup, but now we will measure the motivational levels of the bees when, for example, when they have the goal in their mind, they know that, the blue flower, rewarding flower is over there. There's a ball. Maybe I should use it as a tool or stepping stool. And then, of course, we don't know what is happening in their mind, what they're thinking at the moment. But what if we measure their forces for how much force they're using when they're moving the ball? When having the goal in their mind versus control bees that just play around with the ball without any goal in their mind. So maybe we can use this kind of a very cool microfiber network. We just had a visitor here in Oulu, this professor from Virginia Tech from US who is using this microfiber network to kind of measure the forces, how tardigrades are actually using their legs, for example, tiny creatures, because we don't know anything about their behavior. So they're using this kind of fiber network, and it's possible to use also with bees. So I was super interested in doing some collaboration with this guy. If we can say that okay, these bees that have goal in their mind, they're using more force, they're more motivated in rolling the ball to specific goal. So then we can also measure which specific time they have this aha moment. If we can show there is a peak in their force use when rolling the ball. That would be one indicator. And then of course doing video analysis and machine learning, algorithms to pick up some specific body gestures or anything that they might actually show just before the solve, the moving the ball underneath the flower.
A huge thank you to Professor Loukola for taking the time to speak with me, and you can find the full interview on Patreon along with detailed notes on what we spoke about. I've also been trying to share more about the behind the scenes process of how I make these videos, as well as content that doesn't always make it into the final video. So if you're interested, feel free to check it out, and it's the best way to support the channel long term.